Hello everyone, welcome to the lecture on relations and functions. Hopefully you have some note paper in front of you and you're ready to go. This should be a review for most of you, so I'm going to go through it pretty quickly. You may need to press pause a couple times in order to follow along, or you may be able to fly through it with me because you remember all of this stuff from Algebra 2. So first, consider the equation y equals 2x plus 5. Now, this is a function, and one way to display solutions to this equation is through a mapping diagram. In a mapping diagram, the x values would be the 1, 2, 3, and they'd be on the left-hand side. And so you can see what's happening if you plug 1 into the equation as x, and you would get 7. And so 1 is mapped over to 7. If you were to plug 2 into the equation, you would get 9 for your y value. And if you were to plug 3 into the equation, you would get 11 for your y value. So you're mapping from the x to the y in a mapping diagram. What this creates is it creates a set of ordered pairs. Any set of ordered pairs is called a relation. Any set of ordered pairs. Now, a couple of other definitions. All possible values of the first variable, the x, we call that the domain. And all possible values of the second variable, the y, is called the range. So the domain is the x, the range is the y. So in our example, the domain would be 1, 2, and 3, and the range would be 7, 9, and 11. And you can see how you would write that. Now consider another equation, x equals y squared. Here's the mapping diagram. If x is 1, y could either be negative 1 or positive 1, because negative 1 squared would be 1, and 1 squared would be 1. If x is 4, then y could be 2 or negative 2, and if x is 9, then y would be 3 or negative 3. A function. Now here's the difference. The mapping diagram you have on this slide represents a relation because it's a set of ordered pairs. 1 goes to negative 1, 1 goes to positive 1. 4 goes to negative 2, 4 goes to positive 2. So that's a set of ordered pairs. The difference between a relation and a function is a relationship between two variables such that each value of the first variable is paired with exactly one value of the second variable. So in other words, for every x, there's only one y. In this case, that means that the first equation I showed you was a function, but x equals y squared is not a function, because the 1, in this case, the x equals y squared case, 1 gets matched up with two different things. And in the previous example, the 1 only got matched to one variable. Okay, so here's an example problem. Given the relation, find the domain and the range. Remember that the domain is the x values and the range is the y values. So you would simply write them, the domain, 3, 1, negative 2, and the range, 2, 6, 0. Relations, such as this one, remember a relation is simply a set of ordered pairs, can be shown in three different ways. You can show it with a table, you can show it with a mapping diagram, like this one, or you can show it with a graph. And you have to be able to see and do all three different types. Here's our definition of function again. Remember that a function is a relation, because a function is a set of ordered pairs, but it's a special type of relation. Every element of the domain is paired with exactly one element of the range. So there's one and only one output with every input. Think of a function like a machine. It's a number machine. You put an x variable in, x value in, and you get a y variable out. For every x you get in, you can only get one y out. That's what makes it a function. A couple of notational things. You think of y as the output. The f is simply the name of the function. F is not a variable. You're not multiplying or anything. It's just the name of the function. F is very common. We also use g and h. It could be any name. And the x is the input. Now, determine whether each relation is a function. So is this relation a function? I'll give you a minute. Okay, that should be enough time. Let's take a look at this. If we put 2 in, we get 3 out. If we put 3 in, we get 0 out. If we put 5 in, we get 2 out. And if we put 4 in, we get 3 out. All the x's are different. Every domain is different. So therefore, yes, it is a function. Okay, what about this one? Again, I'll give you a minute. Okay, if we put 4 in, we get 1 out. If we put 5 in, we get 2 out. If we put 5 in, we get 3 out. If we put 6 in, we get 6 out. And if we put 1 in, we get 9 out. In this case, no, this is not a function because the 5 is paired up with two different numbers. Now, graphically, if you have a relation that's given to you graphically, you use something called the vertical line test to help you decide whether or not it's a function. So what you want to think about is if any vertical line passes through more than one point of the graph, then that relation is not a function. So here are some pictures. Is this a function? Imagine drawing vertical lines. If a vertical line, there they are, there's all the vertical lines. Every vertical line only hits the red function line one time. Therefore, yes, it is a function. In this case, again, imagine drawing a bunch of vertical lines. There they are. Every vertical line only intersects the red line once. So yes, it's a function. In this case, there's your vertical lines. Some of those vertical lines intersect the function twice. So therefore, nope, it is not a function. All right, let's do some more. Is that a function? There's your vertical lines. Yes, it's a function. What about that one? There's your vertical lines. No, that one's not a function. One of those vertical lines intersects that red line multiple times. What about that one? No way, that's not a function. It hits it twice. What about that one? Yes, that's a function. The vertical lines only hit each one once. Is this a function? Yes, that's a function. Vertical lines only touch it once. Now, if you're given a function, f of x equals 3x minus 2, a lot of times I will ask you to evaluate the function. Say something like f of 3. We know from the machine before we put 3 in, we see what we get out. So if we put 3 in, we plug it into the machine, 3 times 3 minus 2, and out comes 7. If we plug in negative 2, we plug in negative 2, 3 times negative 2 minus 2, and out comes negative 8. Okay, so the input is 3, the output is 7. The input is negative 2, the output is negative 8. Right? What about this one, h of negative 3? Again, if we plug negative 3 in, we have to square the negative 3, minus, plug the negative 3 in and multiply it by 4, and then add 9. Be careful with order of operations, and you can see that you wind up getting 30. So therefore we say h of negative 3 equals 30. Okay. What about this one? X is the independent variable, and f of x is the dependent variable. So a couple of other definitions that you need to know. And we always think of f of 3 means 2 times 3 plus 5 for this function. And you can see these examples as well. Trust that you're getting it by now. You've seen this before. This is nothing new. Take a minute and answer this one. Be careful with order of operations. Okay, you have your answer. Negative 16. Hopefully you got that right. All right, here's a couple more. Be careful with these. These have variables. Okay, if you plug in 1, you get 2. If you plug in 3a, you get 27a squared minus 6a plus 1. Be careful with the squared. And n plus 1. If you plug in n plus 1, you have to square it. And you also have to plug the n plus 1 in for the x next to the 2. N plus 1 squared, you have to remember to FOIL that in order to distribute the 3. So you have to FOIL it first, then distribute the 3 across, and then you can simplify. That leads us into another example. Okay, so for this one, I'll give you this as an example, and then you can do another one on your own. G of x plus h minus the original function g of x, all of that divided by h. So I'm going to plug x plus h in for all the x's. The first 3 terms represent the g of x plus h. then I had to subtract the original function. So that last parentheses is where I subtracted the original function. Now I have to simplify. So x plus h, I'm going to square that by foiling it. Then I'm going to distribute the 3 and distribute the negative 2 and distribute the negative 1. And I get this. And then finally, I'm going to simplify by crossing out, by combining like terms. And then once I've combined like terms, I can divide out all the leftover h's, and I get my final answer, 3x plus 3h minus 2. Okay, you ready for an example on your own? Start you off with these two. Okay, I'm going to give you the answers. If you don't have the answers yet, press pause until you're ready to see them. For the first one, you get 108. For the second one, plug in the x plus 1s, FOIL it, distribute the 3, combine like terms. Okay, I'll give you another one. Do this one on your own. When you're ready, press pause. Then do this on your own. And when you're ready to see the answer, press play. Okay, here comes the answer. X plus h squared plus 3x plus h, then you have to subtract the original. FOIL everything, distribute the negative, distribute the 3, combine like terms, divide out the h's, and you get 2x plus h plus 3 for your final answer. Now, the last thing we're going to talk about is how do you find the domain of a function? Remember that domain is the set x, the set of values you plug in for x. For the functions that we're going to deal with, there are two, I'm going to call them illegal situations. First, you can't divide by 0. So therefore, the denominator of a fraction at the bottom can't be 0. Secondly, you can't take the square root or the even root of a negative number. When you're asked to find the domain of a function, you can use any value for x as long as the value won't create an illegal situation. And the two situations described in purple are the illegal situations we're going to focus on. So here's an example. Find the domain for this function. Well, ask yourself, is there an x value that's creating an illegal situation? Are we either dividing by 0 or taking the square root of a negative? And the answer is no. There's nothing that causes an illegal situation, so therefore all real numbers is your domain. What about this one? Well, in this case, there is something that will create an illegal. If we were to choose x equals 2, then the denominator would be 0, which is illegal. Therefore, the answer is all real numbers x such that x doesn't equal 2. Right, the does not equal sign. Focus on the bottom. And remember, there's nothing wrong if the top is 0. If the top is 0, that's fine. It's just the bottom that can't be 0. Now here's a square root problem. Now remember, we have to be careful what x's we use, because taking the square root of a negative doesn't happen. So the stuff under the square root has to be greater than or equal to 0. So we take the stuff under the square root and we say it has to be greater than or equal to 0. Set it up as an equation, solve it, and you get x is greater than or equal to 4. So the answer is all real numbers x such that x is greater than or equal to 4. So here's a quick summary. If you're being asked to find the domain of a function, look for fractions or square roots that could cause one of the two illegals to happen. And if there aren't any, the domain is all real numbers. If there are fractions, figure out what values would make the bottom equal to 0, and those are the values you can't use. So the answer would be all real numbers x such that x is not whatever those values are. If there's a square root, the stuff under the square root can't be negative. So set the stuff greater than or equal to 0 and solve. And the answer would be all real numbers x such that x is greater than or equal to whatever you got. Remember, your variable doesn't have to be x. It can be whatever's in the problem. Now, most of this should have been a review for you, so hopefully it refreshed your mind a little bit. When you come to class tomorrow, we're going to talk some more about finding domains, and we're going to do a couple more of those x plus h problems because I know those are always tricky.